Hello class, this is CSE-5250, sections 2 and 60, week 12, spring 2026. I'm Giovanni Orijuela, and let's look at MPI. So we did go out of order in the book. We went chapters 4, 5, and then 3, primarily. But because we went through so much so far, we can get basically started with the Hello World program with MPI. So this is the code here. All you need to do is copy this code, and there you go. That's a full-on Hello World program that uses MPI. Of course, you're going to need to know how to compile it. And of course, we're going to have to step through the relevant lines of code to see what's going on. So on a Unix machine, this is the command needed to compile your program, MPI-CC. And if you are using C++, hold on. If you are compiling this as a C++ program, the command is actually MPI-CXX. But if you're doing this using pure C code, it's just MPI-CC. There is support for Fortran, so you can write MPI programs in Fortran. We're just mainly using C and by extension C++ here, so it's either going to be MPI-CC or MPI-CXX, depending on which language you are using. The rest of the command is going to be the same thing. And again, this is just the command to compile the whole program. So after that, it's -g-wal-o, the name of your executable and the name of your source code file. Now to run the program, it's not just /, rather we have to add a few things before it, and that is MPI-exec-n, the number of processes, and then / the name of your executable. When you run the program, you'll get an output that looks something not unlike this. So this is on PowerShell, and that's Windows. If you're going to be doing this on Windows, I have special instructions later in the video. But either way, you're going to get output that looks not unlike this. So this is with Windows PowerShell. That is Windows equivalent of a Unix terminal. The command also works here, MPI-exec-n. In this case, it is 4 processes. So yeah, that's how we go about compiling and then running the program. If you are new to MPI, chances are you might encounter something like this. What if you don't have an MPI installation on a Linux machine? Well, in that case, you might try to type in MPI-CC, and then you'll find command not found, and you will be given, in this case, for an Ubuntu machine, you may be given one of several commands to choose from to install MPI on your machine. You're gonna have to type out one of these commands. I personally chose open MPI-bin. I cannot demo this because it's already on my Ubuntu machine right now, but you would just go through the install process. You might have to enter your password, your Linux password for this, but basically you type in sudo apt install open MPI-bin, or at least that's the case with me. You're gonna have to follow the on-screen prompts. If it says yes or no, say yes, of course. If it asks for your password, just type that in. Once that is done, if you type in MPI-CC again, and you get no input files, that means it's working, that means it's there. Okay, and then you try it out, and you might get something like this. That just means you are running your program on using more processes than your system can handle. Think of a slot as a CPU core. So if there's not enough slots, you can't run all the processes all at once. There are one of two things you can go around this, and the most obvious one is to just add --oversubscribe to your MPI-exec command to force the computer to run with more processes than there are CPU cores. Or you can just lower the number of processes. This will inevitably hinder performance of your program because there aren't enough CPU cores to run all of your processes. But for something as simple as this Hello World program, it's not really going to matter because it's so short, it's probably going to be okay. In practice, that just means you might need a more powerful computer or possibly an entire distributed system to run your program. But yeah, if we go back a couple slides, the entirety of the program is just this screenshot here. So let's investigate what all that code is doing. Obviously, anything related to MPI is going to be prefaced with MPI in its name. And there are three pairs of functions that we have to take note here. The first one is going to be MPI init and MPI finalize. They both are self-explanatory. In fact, what they do is in the name. MPI init, that just initializes the environment in which MPI can run in. So before you do anything related to MPI, you call MPI init. That function requires you to pass in two arguments, but just pass in null for both of them. MPI finalize, when you're done with any MPI related functionality, you call MPI finalize, and that's it. That's basically the end of MPI related functionality. You cannot call any more MPI related functions after that. It doesn't necessarily mean that's the end of the program. You can do more stuff and then end the program after that. It's just that you can't do any more MPI related anything at that point. That MPI finalize function requires you to pass in an argument, but just pass in null for that as well. In short, you call MPI init before you do anything, and MPI finalize when you're done. Also, these two functions, along with all MPI-related functions, they return an error code in the form of an integer value. I am foregoing this for the sake of teaching, but it's probably likely a good idea for you to want to use those error codes in case something goes wrong with your program. Again, I'm just going to forego that for ease of teaching. Okay, so that's the first pair of functions. The second pair of functions to talk about are MPI com size and MPI com rank. In OpenMP, there's a pair of functions with near identical names: MPI get num threads and MPI get thread num. These two MPI functions are analogous to those two OpenMP functions. But we have to talk about what is a communicator. A communicator is just a collection of processes that can send messages to one another. One of the purposes of MPI init is to define a communicator, consisting of all the processes started by the user. So when we call that MPI exec command, and we say also dash, and we say run this with 10 processes, we are creating a communicator that consists of 10 processes. So all 10 processes are going to be able to communicate with one another. There is always going to be a default communicator that is called MPI com world. So these two functions, MPI com size and MPI com rank, they get information about MPI com world, but there is no reason why we can't define other communicators, but for our purposes here, we're just going to be working with the default communicator. So, MPI com size gets the number of processes in the communicator, and MPI com rank gets the rank, think of it like a process ID for that process in that communicator. So like how we have multiple threads working as a team in OpenMP, and each thread has a unique ID, so do the processes in an MPI communicator. So again, these two functions, MPI com size and MPI com rank, are analogous to the functions in OpenMP. OMP get num threads and OMP get thread num. See what I mean? How those two functions have near identical names? Anyway, in either case, the first argument must be the communicator. again, we're working with the default communicator, so just pass in MPI com world. The second one should be the address to whatever variable you are storing the com size or rank. So you are gonna likely have two separate variables for the communicator size and that process's rank. And that's how you call these two functions. So let's look at that block of code where we have if my rank does not equal 0, else. So if my rank does not equal 0, we are going to execute this code here, else we're going to execute this other code here. So this is something that is common with a lot of MPI programs, and by extension, SPMD programming as a whole. We have some process, likely process 0, that's going to do something, and all the other processes are going to do something else. In principle, whatever it is we're doing should scale with however many processes we have. Put another way, we should be going in with no expectations about how big our communicator is going to be. In short, whatever we write should be able to run with 10 processes, or hundreds of processes, or possibly millions of processes. It's almost always the case that whatever we write, we cannot know in advance how many or what kind of resources are available to us. So whatever we write should scale up and should run no matter what. Doesn't matter if you run it with 10 processes or 10 million processes. It should work no matter what. Okay, now let's talk about what's going on here. So, the meat and potatoes of what you're doing with MPI is, well, message passing. It's literally in the name. MPI stands for Message Passing Interface. So, one process is going to send and another process is going to receive. Now, I have to back up a little bit because with OpenMP, that is just a single program running multiple threads and they all share the same memory. With something like this, we are running multiple processes that may not necessarily be on the same machine. Therefore, we can't have shared memory. So the next best thing is to send messages between processes that are possibly on different computers connected by a network. So that's why we have message passing, because we don't always have the luxury of shared memory. And because this is something that is typically used with distributed networks, our only bet is message passing. Anyway, in either case, whatever we send, anywhere we have a send in a program, there must be a matching receive. Every send must have a receive, and, well, vice versa. Or otherwise, the program won't work. So let's talk about the send function here. It is this function down here. So for all processes that are not ranked 0, they're going to send a message. In this case, they're going to send a message to rank 0. Let's talk about those 6 arguments right now. So the first argument to pass into MPI send, that is a pointer to a block of memory that contains the contents of your message. So it's a buffer. It's a buffer that contains our outgoing message. The second one is your data type. Yeah, so the second argument is your... No, my bad. The first argument is a pointer to the buffer. The second argument is the size of the message. The third argument is the data type. And these are the different data types supported by MPI. Character, short, int, long, unsigned variants of all of your integer type variables, all of your different floating point variables, and byte. The fourth argument is the rank of the receiving process. So if we are sending to process 0, that means that fourth argument must also be 0. It's like how you would write a message and literally put the address of whoever's going to be getting the message. If you don't put an address, the post office is not gonna know where to send it. They might even return it back to you. The fifth argument is a non-negative integer that is known as a tag. That's just used to differentiate messages that are otherwise identical. Say you send two messages and they both are for integer values, but one is used for something else. So we use tags to differentiate between two different, let's say, integers that are being used for different purposes. So let's say one is used for computation, the other one is used for printing. We can use tags to differentiate the two. The sixth argument is going to be the communicator. For our purposes, just pass in MPI com world. Think of MPI com world as a communal Discord server and other communicators as other servers where different processes have different accesses to those different servers. That's the best analogy I can come up with how communicators work. Now, all 6 arguments have an analog for MPI receive. So the first argument is a buffer, but this buffer is going to store the incoming message, not the outgoing message. The second argument is the size of the message. The third argument is the data type. The fourth argument is the rank of the process who sent the message. So when you write a letter and you have to put an address on the envelope, there are 2 address fields. One is the address of whoever sent it. The other is the address of whoever is going to receive it. Except we use those 2 different addresses, or in this case, ranks, for 2 different functions, send and receive. The 5th argument is the tag, and the 6th argument is the communicator. All the same with MPI send, except now we have a 7th argument. For our purposes, just pass in MPI status ignore. So, when you send a message from one process to another, the following arguments must match one another. The tags must match. The communicators must match. And if process Q sends a message to process R must receive from process Q. There are a few caveats regarding sends and receives. If you look at our code here, we have multiple processes doing a single send each. And for process 0, it is running this for loop that contains MPI receive inside of it. So, because of how this code is structured, it is going to call MPI receive for process 1, and then MPI receive for process 2, and then MPI receive for process 3, and let's say this is 99 sending processes, and the 100th one is process 0, who is receiving 99 messages from 1 to 99 in that order. What if process 99 sent its message first? Then that message has to wait for the first 98 messages to be processed, and then for it to get processed. So that is something that can and does happen with sends and receives, and there is a way around that. So if we do not care about the order in which sends and receives occur, then there is a wildcard that we can add in place of that I iterator in the code here. So if you look in the code again, because this receive function is using this iterator I to go from 1 to 99 for the rank of the sending process, we can replace that I with a special tag, and that tag is MPI any source. Each process can take a varying amount of time to finish, so process 0 has no way of knowing which process had actually finished. In this case, you just replace that 4th argument with MPI any source. A similar situation can happen with the tag, so there is also a corresponding tag for that. A corresponding wildcard, I should say, for that. That is called MPI any tag. So these wildcard arguments can only be used by the receiver, not the sender. Also, there's no wildcard for communicators. There is no such thing as an MPI any com. Only MPI any source and MPI any tag. So, yeah, that is the basics of what we're going to be doing. And I'm going to show you the next set of slides now, just for preparation of what our next programming assignment is going to entail. Let's look at that real quick. So, yeah, we're doing the trapezoidal rule once more. But it's going to be a lot trickier to program with MPI, and I'll show you why in a little bit. We did this back in Chapter 5, but now we are doing this in Chapter 3. Remember, we did the textbook out of order, so we did Chapter 5 first and then Chapter 3. So, the requirements of what we're doing is going to be the same anyway. We have to define a program that contains this trap function as well as another function that defines our function f of x. That trap function has to do the following work. It must distribute the work of calculating each trapezoid's area and then gather all of those areas into one single variable. But it is basically the same process as we were working with OpenMP, so the steps are going to be the same. Partition the problem solution into tasks, identify communication channels between tasks, aggregate tasks into composite tasks, and then map those onto cores. Your code would look something like this, but what we're going to do later instead is we're going to hard code the n so that is logged at 1024 trapezoids. Remember, the more trapezoids the better, but we're just going to log it at 1024 instead. Note that there are going to be multiple global and local variables involved here. Take this time to try to figure out which is which. And of course, we're going to have code that is not unlike our Hello World program, where we have, if my rank equals 0, we're going to do a send, and then if my rank is anything other than, if my rank is 0, we're going to do something else. So it's going to be in this case, it's all processes other than process 0 doing a send, and process 0 doing a receive that is within a for loop. So if you can imagine this working with 4 processes, each process adds the area of 256 trapezoids. And when we're done, we can just, of course, print it out. Of course, we still need our trap function, which calculates the area of multiple consecutive trapezoids and then sums them together, and our function f, which we're just going to define as f of x equals x squared. When we're done, we can just run the program as we would using the command mpixec. And now we get to deal with one of several issues with MPI. We would like the program to run with more than just hard-coded values. We hard-coded the number of trapezoids to 1024, but there's nothing about that is special. We would rather like to run it with any arbitrary amount of trapezoids. So in terms of output, all processes in MPI ComWorld have access to standard out and standard error. That just means any processes can print f and call any other similar print functions. So all the processes are able to print output to the screen. But what about input? Because depending on how we code this program, you might have the user be prompted to enter in the left endpoint, the right endpoint, and the number of trapezoids for the area calculation. which process is going to do that? Well, most MPI implementations lack any automatic scheduling, so any output printed to the console will just basically be whatever order it's going to be. This is non-deterministic output. So we're talking about the output here because all the processes in a communicator have access to print F. They'll just print F at whatever time the CPU scheduler deems appropriate. And there's no way to predict what that's going to be. There's no rhyme or reason as to the order in which processes do their output. But we are talking about input here. Well, most implementations of MPI only allow process 0 to have access to standard input. If any other processes need information that is passed to process 0 this way, we just send it via message passing. So, in short, we have this communicator of processes. We don't know how many processes there are. It could be like 10, it could be like 1,000,000. But process 0 is going to be in charge of receiving user input. Once it receives that information, it can then send that information to all other processes. But all other processes have access to printf, so they can just print f anytime they want, in an order that is not going to be deterministic at all. So how do we deal with I/O? Well, we're going to need another helper function for that. Let's call it getInput. So this is a helper function that, when we call it, we have process 0 say to the user, enter A, B, and the number of trapezoids. And then we use scanf to get those three values, storing them in A, B, and N. And then, for each of those values, we must then call MPI send. You see where this is going? It's the same exact structure as we had for the Hello World program a few slides ago. So we have one block of code that is only ever executed by process 0, and then another block of code that is executed by all other processes. In the case of all other processes, it's going to be a receive, and another receive. One each for our three values, that is A, B, and N. So, as a reminder, only process 0 is able to prompt the user for user input. But now it is up to process 0 to send this information to all other processes. And this is such that we can get one process. Okay, so this is such that we can get process 0 to participate in doing all the work. If you recall how we coded things back with pthreads, we had one main thread that was unable to participate with the work. In this case, we have, if you pretend we have 4 processes calculating the area under a curve that is partitioned into 1024 trapezoids, 3 processes just have to do calculations. But process 0 has to receive this input for A, B, and N, and then send it to all of the process, and then calculate its share of 256 trapezoids. And because this is one function in which we must pass in rank, column size, A, B, and N, when we do user input, all we gotta do is say get input and then pass in rank, column size, and A, B, and N, and that's it. And through that, we no longer have to hard code N, or A, or B for that matter. So now we're getting into what is now known as collective communication. Here's where things get interesting. So our trapezoidal rule program operated using the following steps. For each process, compute a local area that is a portion of the area under the curve. For all processes other than rank 0, send a message that contains that process's local area to process 0. For process 0, receive a message from all other processes that contain the process's local area, then get those areas with process 0's to get with process 0's local area to get the total area. The thing is, if we have a send in a for loop or a receive in a for loop, that is actually not the most efficient way to send anything in MPI. Rather, this is on the section for tree structured communication. And I gotta explain what's going on here with an animation. So here's a simple example where we have 8 processes and they all have a value that must be added to process 0. So we have 8 values and then this first value here, that's the total. So what we could do, in principle, having a receive in a for loop is like this. So we are going to iterate through values 1, 2, 3, 4, 5, 6, and 7, and value 0 is going to be the total. So the first thing we add is the value value 1 to value 0, 2, 3, 4, 5, 6, 7. And that is 7 addition operations in total. That required 7 steps. Now there is a more efficient way. Check this out. Instead of having it such that we have this one value incrementally adding values from all other processes, we just have one half of those processes add something from the other half. And just like that, we performed half of our required additions. And now, with all the processes that are left over, we do it again. And again. So we just did 7 additions in the time it takes to do 3. Theoretically, at least. And that is the basis behind tree-structured communication. So if you imagine these are processes 0, 1, 2, 3, 4, 5, 6, 7. Process 0 adds a value from process 1. Process 2 adds a value from process 3. Process 4 adds a value from process 5. Process 6 adds a value from process 7. And that's the first step of all these additions. The second step is process 1. Process 0 adds something from process 2. Process 4 adds something from process 6. And then the next step, it's process 0 adds something from process 4. And that's it. We've just added everything in 3 waves of additions. And the beauty of this is it scales up. If we had 1024 values to add, spread across 1024 processes, if we just did that receive in a for loop configuration, that would require doing 1023 additions one by one. Not good. But if we did it in this tree configuration, in the time it would take to do 10 additions, we can do all 1024 of them. That means we can do all that work in 1/100th of the time. And of course it's going to scale up. And in general, using this tree structure, if n values are to be added, the time needed to add those values using a tree structure is on the order of base log 2 of n. So 1000 additions takes 10 steps, 1 million additions takes 20 steps, 1 billion additions takes 30 steps, and so on. Of course, it's going to be a challenge to code this addition process in this tree structure. It would require doing lots of sends and receives, but MPI already has a function for us, and that is MPI reduce. A global sum function still requires communication, but it's going to be different from our point-to-point communications that we have been doing so far. So, doing just sends and receives, that is just point-to-point communication. But what we are doing is collective communication. Communication across a whole communicator. And MPI reduce is one of a few functions meant for collective communication. By the way, you probably may or may not have heard this yet, but as a general rule of thumb, or possibly as a reminder, every 10 powers of 2 roughly corresponds to 3 powers of 10. In other words, 2 to the 10th power is about 10 to the 3rd power. That also means 2 to the 20th power is about 10 to the 6th power. And 2 to the 30th power is about 10 to the 9th power. It doesn't perfectly match, but it is generally a good rule of thumb that works for small amounts, relatively small powers of 2 and powers of 10. At some point, it just that discrepancy just explodes, but we don't really have to worry about it in this context right here. So, since we're doing communication, where we have one process receive something from all other processes in the same communicator, we're doing collective communication. MPI supports different types of reduction operations, which is listed in this table. Like how in OpenMP, we also had reduction operations. For our running example, we're just going to be doing addition, because in the program for the trapezoid rule, it's just addition after addition after addition, and we are just adding it to a running global total. But it's far from the only reduction operation available to us. So here is these are the arguments for MPI reduce. It's going to require the following arguments. The first argument is the address of the local value to be added. The second argument is the address. Okay, so the first argument is the address of the local value to be added. The second argument is the address of the total. The third argument is the number of values being added. If we're just adding singular values, just set this one to 1. The fourth argument is the data type. That's basically the previous table here. So these are the different data types. The fifth argument is the reduction operation being performed. Okay, I actually mixed it up. These are the reduction operators for MPI. There was another table previously that showed the various data types MPI supports. The sixth argument is the destination process. Basically, which process is carrying the total. And the seventh argument is the communicator. So there are 7 arguments you are to pass in with MPI reduce. That means, with the knowledge of MPI reduce, we can take some block of code that looks like this and replace all of that with just one line of code. How neat is that? So, this setup where we have a receive within a for loop, which is inefficient, it does the same thing as this reduce function, but faster. Hey, remember that third argument in the MPI reduce function? We set that to 1 because we're just adding singular values. If we set that to, say, n, where n corresponds to the size of an array, then MPI reduce can perform operations typical of linear algebra. So we can do stuff such as vector addition. So with one change, we can go from adding singular values to adding vectors. Also, there are other ways we can do point-to-point communication, but before I get to that point, there are a few rules I have to talk about. All the processes in the communicator must call the same collective function. For example, if we call MPI reduce on one process while calling MPI receive on another process, that's erroneous. The program will crash. Also, the arguments passed by each process to a collective communication must be quote-unquote compatible. if one process has the destination be 0 and another process has the destination be 1, the program will also crash. Also, that second argument in the MPI reduce function is only being used by the destination process. But all processes still need to pass in something, just pass in null for that. So, if we have that example of 100 processes, process 0 calls reduce, but so do processes 1 through 99. It's only process 0 that passes in something, that has to pass in something for the second argument. All other processes still have to pass in something, even if it's null. Point-to-point communications are matched based on the tag and the communicator, but collective communications don't use tag. Instead, they are matched by the communicator and the order in which they're called. And one final caveat. In some languages, you can use the same buffer for input and output, but that is considered illegal in MPI. It's illegal because that involves something called aliasing of an output argument, because the input and output arguments refer to the same block of memory. This restriction was added to MPI because MPI was made to work with C and Fortran, but Fortran prohibits aliasing. So something like this would work with C, but not Fortran. So the creators of MPI just said, okay, this is not allowed in either language. Okay, so now, what if? Okay, so now we have this tree structure in which all of our processes are sending something to process 0. What if we need that value again for another communication? No, for another computation. That means we have to do, after a reduce, the reverse of a reduce, which is, by the way, called a broadcast. So if we just did this half here, that is called reduce. If we just did this half down here, that is called broadcast. But what if we wanted to do a reduce and then a broadcast? Well, that is its own collective communication called all reduce. We have this tree structured communication here, followed by the same thing but in reverse. This topology is sometimes known as a butterfly for obvious reasons. And the arguments for all reduce are as follows. If I can get my face in here properly, there we go. So all reduce is just a variant of MPI reduce. So all reduce is just a variant of reduce. And unlike MPI reduce, there is no destination process. Every process gets the result. So let's go to what you are passing into an all reduce. The buffer for the incoming data. So you have the input, the output, the count, the data type, the reduction operator, and the communicator. So that's all you need for an all reduce. But what if we just needed this? The part that is known as a broadcast. Well, that is called bcast in MPI. So this only requires 5 arguments. The buffer in which we have our outgoing message, the count, the data type, whoever is sending the message, and the communicator. So all of these correspond to the same arguments with MPI reduce. So, although we won't be coding this just yet, when we do, we can go back into the code and realize that this code is basically one process repeatedly calling send to all other processes. So that's a lot of point-to-point communication that we can simplify into collective communication. So something like this can be simplified into this. So just these 3 lines of code and this code that does the I/O, all of this corresponds to all of this, but better, but faster. So that is what we're going to be doing in our next programming assignment. For now, I'm going to show you how to start with your first MPI programming assignment, and that is the Hello World program. Give me a minute. Alright, I just moved my face cam, so I'm going to start this on a Windows machine first. So I'm going to first add a, not existing item, but rather new item. So add new item, and I'm just going to call it main.cpp. There we go. There we go. And I am going to start writing in some code. Include mpi.h. It's already throwing an error. We'll fix that in a little bit. Next, we're going to write in our other directives, and that is include standard io.h. You'll note that this is C code, but I'm putting it in a C++ program, and that's okay. C++ programs can run C code, but not the other way around. And then include string.h. I'm now going to define a constant variable that's going to define the size of my buffer, because we're going to use a character buffer to store our message that is going to be sent from one process to another. So constant int max string equals 100. There we go. Now I'm going to write this. I'm going to write my main function. There we go. And now I'm going to create my character buffer. Character creating array size max string. That is our buffer that's going to store either our outgoing message or our incoming message, depending on which process is which. Now I'm going to define 2 variables, int com size and my rank. There we go. Or we can just define it on 2 separate lines. This way also works. And now, I'm actually going to comment on my code. Not like that, though. We're going to call now the first of our MPI functions. The first of which is, of course, going to be MPI init. And already it's causing issues. Let's actually fix that right now by talking about how you can set up a Visual Studio project to use MPI. It's actually a 2-step process. The first step must be done if you have never installed MPI on your machine before. Let's talk about that now, but I have to pull out a different document. Okay, so there is a document that my brother has kindly provided. It is how to set up MPI on a Windows machine for Visual Studio. So, you want to go to this link here that will take you to a download for Microsoft MPI. When you click this link, you'll find, when you click this link, you're gonna have to download 2 separate installers, msmpi-setup.exe and msmpi-sdk.msi. You need both of them. Once you download both of them, you're gonna want to run both executables. Well, both installers. One's an executable, the other is an installer. You're gonna want to say yes to any prompt that says, do you want this to make changes to your device? And once you're done, one of them is for running MPI programs, the other one is for making MPI programs. You need both. So take the time to download both of them and then run both of them. Because once you do those two steps, you never have to do them ever again. Unless the installers get updated. I'm actually gonna go through these steps right now, so let's see if I can actually do that. Okay, so this is Microsoft MPI. Down here is the download link, Microsoft MPI version 10.1.3. If I click that, there's a big download button in the middle of the screen. At least it's in the middle for me. I'm gonna click download, and there are the two files I need. So I'm actually not gonna go through the steps of downloading and installing them because one, I already have them installed, but two, I've had bad luck trying to record myself running an installer, and I think the only way for me to do that is to have a video capture card. So I'm just not gonna do that. But again, you do need both installers. Alright, let's continue. So this next step, I'm actually gonna demo with my project here. Let me just finish writing out this MPI init function. Remember, there are two arguments you're passing into MPI init, and you can just leave them as null for both. But right now, the editor is screaming at me, I have no idea what MPI is, and I have no idea what MPI init is. Let's tell it what it is. Okay, so now we have this Visual Studio project, but we have to tell it what MPI even is. So I am going to go up here, the Project tab. Click Project Properties down here. You'll get this window that is basically the same window with telling your program to work with OpenMP. So if you recall that process, that is just clicking the C/C++ and actually no. Yeah. In here, if this was an OpenMP project, you just have to go to C/C++ and language and then turn on OpenMP. We're not doing that here. We're doing something else. So let's go back to C/C++. And what we want to look for is additional include directories. I'm actually not seeing that right now. Let me just see if it's... Yeah, it is down here in general. C/C++ and then general. That's where it's appearing for me. There is a slot for additional include directories. If I click this drop down, it says edit. I'm going to click that and it's going to show another window here. When you run those two installers, there is likely going to be a prompt for where to install your where to install your files. And those files are going to be for the API for developing MPI related programs. Chances are you're not going to change the install location. But when you undergo this install process, take a mental note of where those files are going to be installed because you need to know them for this next step here. Alright, so let's click this blank space here and we get this little ... button. I'm going to click that and it's going to open select directory. For me, I'm going to go to this PC and first I'm going to double check the C drive to see if it's there, and if it's not, it's probably going to be in one of my other drives. I'm going to go to the C drive and I'm going to go to program files x86. I'm going to look for Microsoft SDKs. There it is. And okay, there it is. That's the MPI folder. Inside that is an include folder. select the include folder, and down here, actually no, I'll just shrink it. Click select folder, and then click OK, and then click apply. We are not done yet. That is actually step 1. Step 2, we have to add additional library directories. So for that, go to linker. Look for additional library directories. Click the drop down, click edit. You'll get a similar pop-up as before. Click the blank space, click it again, click the little ... button. We're gonna go to the same location as before with the include directory, but we're gonna go look for the library directory. So it's C drive again, program files x86, Microsoft SDKs, MPI, lib. Now, there are 2 library folders here, x86 for 32-bit programs and x64 for 64-bit programs. What you're going to choose next depends on whether this up here says x86 or x64. In my case, it's x86, therefore I want the x86 folder here. Select folder, click OK, click apply. There we go. That is the second step. The final step is in linker again. So under linker, go to input, look for additional dependencies, click that, click edit, and we're gonna type in msmpi.lib. There we go. Click OK, click apply, click OK. There we go. And just like that, we have a C++ project in Visual Studio that uses MPI. So I'm gonna quickly go through the process again. Go to Project Properties, under C/C++, go to General, and look for and add the folder for the MPI include folder. Then go to linker and do the same thing for additional library directories. That is going to be either an x86 folder or an x64 folder, depending on whether your project is 32 or 64-bit. And then finally, go to input, go to additional dependencies, and just type in msmpi.lib. And that's it. Yes, that took a while, but that's what it takes to get MPI to work here. And now, as you see, we no longer have errors in our code. That means you can code the rest of our dang program. Okay, let's go. Okay, let's continue. So now we have MPI working. If I just go down here and type in the last 2 lines of code, MPI, finalize, and then return 0, and I press Ctrl-Shift-B, that's going to build the program. And if you look down here in the bottom corner of my screen, it says build succeeded, but also throws a few warnings because there are some variables that I never got to use. But the fact that it built means that the program was successfully compiled by Visual Studio. Let's continue the rest of our program. So that is MPI size. The communicator is MPI world, and we're gonna pass in the address of the variable size. There we go. And the next function to call is MPI rank, MPI world, and address of my rank. There we go. And now we get to write our code. this if else block of code here is going to do one of two things. If it's not process 0, send a message to process 0. If it is process 0, receive a message from all other processes. Let me just complete the logic here. So let me add the condition my rank does not equal 0. So the one thing you need to know about this is that this is not one program that we're going to be running. It's going to be multiple instances of the same program. So you have to think about this as though you are... So it's a little tricky to think about because it really is just multiple instances of the same program, running different things based on what rank it is. So let's finish it up right here. sprintf is, we're going to use that, but rather, no, it's sprintf underscore s. And we're going to use that to format our message that we're going to be sending to all other processes. So I'm going to pass in our greeting buffer, and then I'm going to pass in the message, greetings from process %d of %d exclamation point. And then, because those %d's are placeholders, I must pass in, well, it's going to be some rank out of whatever our com size is. So it's the things to pass in now are my rank and com size. So there we go. This would be greetings from process such and such of however large our com size is. And that is our message stored in the greeting buffer. Now, we have to send it. So that's going to be npi send. Pass in the buffer that contains your outgoing message. Pass in the size of your message. So that is going to be however large your message is. So we're going to use strlen and pass in greeting. That's going to give us the size of our message. But we have to add 1 to that because this is a null terminated message and we need one more character to capture that null terminator. Otherwise, it's just going to capture whatever random garbage is coming after the rest of our message. Well, coming after our message. So the next thing we pass in is the data type of whatever it is we're sending. So this is character, so that is npi character. The receiving process is going to be process 0. We don't have any text to worry about, so I'm just going to pass in 0 for that. And the communicator is npi comworld. There we go. So that's the send. Now it's time for the receive. Just for fun, I'm gonna write in an extra printf statement here, and that is greetings from process 0. And that's it. Okay, that's just extra stuff that I added just to show that this is process 0 working. Now, I'm just gonna write the receive function, and then I'm gonna write the for loop around it. So, npi receive. Now, the first argument is going to be the buffer. So, all other processes are using the buffer to write the outgoing message. But process 0 is going to use the same buffer for the incoming message. It's going to be however large it's going to be. We don't know how big it is, but we do have an upper bound of the message size, and that is max string. So I'll just pass in that. And the message is null terminated, so it's going to terminate at wherever that null character is. The data type is still going to be npi character. For the sake of example, I'm going to say that this is coming from process 1. I'm going to have to change that variable in a little bit. The tag is still going to be 0. the communicator is still going to be MPI com world, and the status is something that we're not going to be worrying about, so I'll just pass in MPI status ignore. There we go. After that, I'm going to print out that incoming message. So I'll just write it like this. Print F, and then process 0 receive the message, and then %s, and then \n to indicate a new line. And because that's a placeholder, we need to pass in greeting. So now it's going to print out process 0 receives the message, and then it's going to reprint the message. But now we have to wrap this in a for loop. So the simplest way to do that is to say for int I equals 0, I is less than com size I plus plus. And I'm just going to wrap these two lines of code in some curly brackets. And then realize there are some problems. 1. Now, process 0 is going to receive a message from itself. That's not going to work. So instead, int I equals 1. There we go. That's problem number 1 solved. Problem number 2 is, I had hard-coded the rank of the sender to be 1, but it's going to be this I here because we're iterating from 1 to however large the com size is. So there we go. That is our whole program. So I'm going to build this real quick. Build succeeded. And now I get to run it. So I can just use the local Windows debugger, right? Not quite. If I just hold Control, if I just press Control F5 to run the program, it's just going to run with one process. No, we want it to run with multiple processes. So here is the process of steps to do to get it to run with multiple processes. Make sure you press Ctrl-Shift-B to build your program first. Then, click this solution up here and open folder in File Explorer. It's going to open the project in File Explorer. Somewhere in here is going to be a debug folder. It's here, but if this were a 64-bit program, there would be an x64 folder, and inside that is going to be our debug folder. Either way, open the debug folder, and here's our executable right there. I'm going to type PowerShell in the address bar, and now I'm going to type our command to run the program. And that command is MPI exec -n. I'm going to run it with 4 processes, and I'm going to say the name of the executable. That is CSE-5250 underscore SPR2026 underscore MPI underscore hello.exe. Press enter, and there we go. Greetings from process 0. Process 0 received a message. Greetings from process 1, 2, and 3. I'm going to do it again with 10 processes. And now, process 0 received a message in order from process 1 to 9. So it works. Nice. Okay, so for your first MPI assignment, you will be basically more or less doing exactly what I did, where we have all processes not ranked 0 send a message to process 0, and then process 0 calls receive in a for loop, and then prints out the incoming message that way. Part 2 has you flip it around, so all other processes receive from process 0, and process 0 is doing the sending. That is rather easy to do, and I'll just do it really quick right now. So what I'm just going to do is I'll copy all this code. and then I'm just gonna comment out all that code. No, I'll comment it out. I'll comment out like that, and then string everything like that. And now I get to flip this around. So now I'm just gonna rearrange some code here. So So instead of the I in here, that now needs to be 0 to denote that this process is receiving from process 0. So now we have to do some changes in here. So this 0 here must now become I. And I'm going to do another change here. Process %d receive the message, and then %s. I have to change this a little bit more, and I have to add in my rank. So process %d receive the message, and then %s. So process 0 is going to say greetings, and then it's going to send a message to all other processes. So we could probably simplify this even more, but I'm actually not going to do that. It's just a little easier that way. But the idea is, process 0 is going to send a message to all other processes. All other processes are going to receive. So this program here is now the reverse of the previous one, where instead of process 0 receiving something from all other processes, it's all other processes receiving something from process 0. Let's try it out. If I press Ctrl-Shift-B, I'll build the program again. And to run this program again, first I'm going to type in clear, and now I'm going to press the up arrow key to get that command again. There we go. Process 3 received the message, greetings from process 0 of 10. Process 4 received the message, process 1 received the message, process 2 received the message. And these messages are coming in whatever order they came in. And that is not determined, and that order is determined by the CPU scheduler, and for our purposes that is non-deterministic. We cannot know ahead of time the order in which these messages are being received. So every time you run the program, again and again and again, it might be a different order. So check this out. In the first run, it was process 3 that printed first. It was then process 1 that printed first again, and then process 2 printed first again. There we go. So yeah, that is just a slight modification we can do to understand how sends and receives are gonna work. Oh, by the way, what I'm gonna do next is a slight modification that you're not really gonna be doing here, but I want to show it for the sake of completeness. So I'm just gonna comment out this code, and now I'm gonna uncomment all this code again. So remember I had this I in here, and that meant that process 0 is going to receive a message in the order of rank. But if I did not care about who sent what, if I do not care about the order in which I receive messages, I can just replace that with MPI any source. If I build that program again, and then recompile it, and then rerun it, now process 0 is going to get a message and then print it based on whoever was able to send it first. So if I run this multiple times, you'll see that the order is going to change each time. And again, that's because the order in which these processes run is non-deterministic. We cannot predict it ahead of time. In other words, it's just going to be basically random every time we try to run it. But it works. So, that is not part of your programming assignment, but this last part is. We're going to be working with broadcasts and reduces in the next programming assignment, but I want to at least have you try out the broadcast at this time. So I'm going to clear, and then I am going to modify the code once more. So I'm going to comment out all this code once again, hide, 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 and then uncomment all this code down here, and instead of oops, I commented out more code than I needed to. Let's fix that. There we go. Alright. Alright, let's think about how we can get this code to work with a broadcast. First, I'm just gonna comment out everything. Actually, no, not like that. Comment out everything, and let's think about it. We have NPI bcast, but every process must call broadcast. Every process must pass in a buffer greeting. Only one process is going to use that greeting buffer. That buffer is only going to be used by one process. All other processes must pass in something, but for the sake of consistency, all processes are going to send in the greeting buffer, even though it's only going to be one process that ever does anything with it. We're going to pass in the size of the buffer. So in this case, I had it written slightly differently in the homework, which was size of character times 100. But I think we can get away with just passing in max string. And if this doesn't work, then I'm gonna have to pass in the size in a different way. The character data type, that's a data type. The sender process is process 0, and the communicator is MPI com world. There we go. Okay, but there's still a problem. I did not even assign what this greeting is going to be. So for me to work with this code, I'm going to have to copy this line of code here and paste it in here. But the problem is, process 0 is the only process that has to put together the message. So I'm going to write an if statement here. If my rank equals 0. And then I'm just going to wrap this code like that. I'm also going to add in another another print statement just for completeness. Actually, there's probably a way for me to simplify it, but I'm just not gonna. Don't do that. I'll just add the print statement. So print f there we go. Process 0 has prepared a message to send to all other processes. So now it's throwing a warning. That's just a warning. We can just ignore it for now. Okay, so process 0 has prepared the message, and now all the processes are gonna call broadcast. So now, what's going on is this. Process 0 is using the greeting buffer to store the outgoing message, but all of the processes are going to use the same exact buffer to hold the incoming message. So that's why everything must use the same greeting buffer, even though it's one process that's doing something different with it. Okay, so now we send the message. Now we have to print that message. So let's go back to that code, put that on my other monitor real quick, and there we go. Alright, so we need another if-else block here. So if my rank equals 0, I'm gonna say print f I'm just gonna say process 0 has successfully sent a message. So if my rank equals 0, process 0 has successfully sent a message. It's possible that this broadcast may fail. In this case, this printf statement might not really make sense. So if that is the case, we would then just use whatever error code came out here to determine whether to say this or process 0 has failed to send a message. For now, I'm just gonna ignore all that. So I'm just gonna type in else, and then I'm gonna write in the code that all other processes are going to execute. So that is print f, and then in quotation marks, process %d has received a message, %s, and then \n, and then because we have two placeholders, those must be my rank and message. There we go. No, not message, I meant greeting. My bad. Okay. I'm gonna build that program. It's saying this is uninitialized. We're not gonna worry about that right now. But now, I built the program. Let's see if it works. This is with 10 processes, and it's going to be the same setup as the program from part 1 of your assignment, except we replaced the point-to-point communication with the collective communication. In other words, this should work the same as before. And it did. So process 0 has prepared a message to send to all of the processes, and then process 0 has successfully sent a message. All of the processes received a message, greetings from process 0 of 10. And it's 0 of 10 because it was process 0 that had this greetings from process %d of %d. So it's going to be the same message being sent out to everyone. But yeah, that is your Hello World program in using MPI, using point-to-point communication, and then with one of several different collective communication functions. Now, that's basically the basic gist of what you're going to be doing with your first programming assignment. Now what I'm going to do next is do the same thing in my Linux virtual machine. Okay, so I went through all the effort of typing out the program up here. So it's literally the same program as the one in Visual Studio here. Alright, now let's save that and let's open our terminal so we can compile this bad boy. The command to compile the program is mpicc -g-wall-o. The program name is just going to be hello, and the source code file is hello.c. If I press enter, okay, it threw an error because I just directly copied the code from the one for visuals. So I just directly copy the code from Visual Studio, and in this case, this should not be sprintf. Rather, it should not be sprintf_s. It just should be sprintf. If I tried to use sprintf in Visual Studio, it'll say something like, don't use this, use sprintf_s because security purposes. So I'm gonna save that again, and then I'm going to try to run the program, or time to run the compiler again. There we go. And just for completeness, actually no, I'm not. I don't want to show the C++ version just yet. Rather, actually maybe I can. If I type in mpicc, I get gcc fail error no input files. If I try to type in mpicxx, I get the G++ version of that, no input files. So if this is a C program, it's mpicc. If it's a C++ program, it's mpicxx. But the rest of the command to compile is going to be the same exact thing. Okay. So we have the program compiled, and now we have the executable. To run the program is mpi exec. If it's just typed that by itself, mpi exec could not find anything to do. And that's because I did not write the rest of the command. Let's do that. mpi exec -n. We're gonna run this with 10 processes. And I'm gonna type in /hello. And I'm gonna press enter. And now I have this message, not enough slots. So there are one of two things I can do. I can reduce the number of processes to run by changing 10 to say 6, because this is a 6-core virtual machine, or I can just force it to run with multiple processes. Anyway, I'm going to do the latter. I'm just going to add the oversubscribe tag here. Okay, there we go. Received a message from process 534912678 in that order. And that's because in this code here, I had left in the any source wildcard in here. So yeah, that's the process for writing out your... That's the process of writing and then compiling your MPI program on a Linux machine. Doesn't matter if it's a virtual machine like this, or if you have some way of doing this on a Windows machine. There is a Windows subsystem for Linux that lets you do Linux-related things on a Windows system without having to use a virtual machine. Or you can just do this on a Mac, because that would already count as a Linux machine, or you can just do this on the lab computers, because there are lab computers that are Linux machines. But anyway you're able to do this, now you know how. Right? And that's going to be it for the... Yeah, that's going to be it for the assignment itself. You're going to be writing the Hello World program in one of three ways. The first way is to have process 0 receive a message from all of the processes. That's part 1. Part 2 is having process 0 send to all other processes. And then part 3 is to take the program in part 1 and replace the point-to-point communication with an equivalent broadcast. So yeah, that's all you really need. So part 1 does not require you to add in the source code, because I already gave you the whole program to write out. What we're doing is just making tweaks to it to change how it works. And in each case, I have you running with 8 processes. So if you don't have 8 CPU cores to spare, just force it to run by adding the oversubscribe like that. Okay? That's going to be it for this video.